The topic of this video is binomial distribution. So you might be saying, what is a binomial distribution? Well, if you think about the word distribution, you can think about the word distributed. Well, a distribution is how data is spread out in statistics. And there are certain categories of distributions based on certain conditions, and binomial distribution is one of those. Here are some examples of binomial situations. Tossing a coin is a binomial distribution. It can be made into a binomial distribution, and the reason is because there are two possible outcomes. You will either get a head or a tail if you toss a coin. Gender of children in a family is a binomial distribution. If you have a baby, you're either going to have a male or a female. And then machine parts, whether they're defective or good and working, there are two possible outcomes for that too. Shooting a basketball, either you make the basket or you miss the basket. So those are some examples of binomial situations. So a binomial experiment has a few more conditions it has to meet. So for starters, there are n-identical trials. And if we think about the example of tossing a coin, every time you toss a coin, it's the same. So however many times you toss the coin, that's my n, each time is going to be identical or the same. The trials are independent of each other. So if I toss a coin the first time and I get a head, the second time I toss the coin, it doesn't matter what I toss the first time. I still have a 50-50 shot of getting a head or a tail. And then the third one we talked about briefly is each trial only has two possible outcomes, right? Heads or tails in this case. And then the probability of the two outcomes remain constant. So if I toss a head the first time, the second time I toss the coin, it's still 50-50 whether I'll get a head or a tail. Let's look at a few examples and determine if these are binomial distributions. So the first one, if we treat 863 subjects or patients with Lipitor and ask, how do you feel? Is that a binomial distribution? Well, you have to think about that. What are their possible answers? Well, they could say, I feel great, or I don't feel very well, or I feel worse. So because there are so many different answers, it is not a binomial distribution. Whoops, I got to change my pen. That is not a pencil. So no. All right, 15 governors are randomly selected from the 50 governors currently in office, and the sex of each governor is recorded. So if we look at governors from 15 governors from 50 states, and we record their gender, we have two possible outcomes, male or female. So this could be made into a binomial distribution. 200 statistics students are randomly selected, and each student is asked if he or she owns a TI 84 Plus calculator. So what are your possible answers here? They are yes and no. Either I own one or I don't. So this is also a binomial distribution, or could be made into one. So binomial probabilities has its own notation and formula. This requires a calculator, so we're going to go over this in class, but briefly, the notation is the probability of the number of successes that we're looking for. So I'm just going to highlight this as I go. That's what this means, the probability of however many successes we're looking for, is equal to how many different ways or combinations there are for that to happen times the probability of success to the number of successes times the probability of failure to the number of failures. We will go over this in class. I just don't have a calculator in front of me, and I don't want to record a video, so I will show this in class. So what we're going to use is a table from your book. You have a table of binomial probabilities. It is in the appendix at the back of your book on page A3. So we're going to use a table. So our first example of calculating a binomial probability is, according to the Gallup organization, 65% of Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what's the probability that exactly 10 favor the death penalty? So the first thing we're going to look at, the first part of our example, is we're looking for the probability of 10. And if first thing I need to do is identify some important information in my problem. You'll recall that n from the previous page is the total number of trials. And if we look here for the total number of trials, we'll find that here. We have a sample of 15. It could also be thought of as your sample size. And then we need, we can find the probability, that's P. All right, and the probability is 65%. We always change that into a decimal when we're calculating probabilities. The other thing we can find is Q, that is the probability of failure. You won't need it when you're using the table, but if you ever have to use the formula, you might need it. So that's 0.35. And in the case of my first problem, we're looking for x. That's the number of successes. That's 10. So in the first section. So I'm going to have you calculate these from the table for your quiz today and for our examples. If I go to the table, I have to go and scroll through. There are multiple pages. I'm looking for n equals 15 because that is the number of trials we have. The other thing I'm going to look for is my x value here. Lost my pencil. And we said that the probability of, we were looking for the probability of 10. That's here. And the final thing I need to look for is my probability. That's here, and I'm looking for 65%. So I don't have 65%, I have 60 and I have 70, so I'm going to have to average the two when I find the column that I'm looking for. So if I go across here and find out where these intersect, it's going to be here. So I need to take the average between 0.186 and 0.206. And when I do that, I get 0.196. So the probability of 10 is about 0.196. If I do that in a calculator, I'm going to get a slightly different answer, but that is, as long as it's really close. If you're taking a test or a quiz and you calculate it using a table, you just have to write a little note that you're using a table. because it can be just slightly different. So the next probability we're going to look at is the probability that no more than 6 favor the death penalty. So again, these can be tricky. The no more than, I always talk myself through that. Is 6 no more than 6? Yes. Is 5 no more than 6? Yes. Is 7 no more than 6? No. So I know that I need everything. I'm looking for the probability of 0, plus the probability of 1, plus the probability of 2, plus the probability of 3, plus the probability of 4, plus the probability of 5, plus the probability of 6. I need all of those. And it's really important not to forget the probability of 0. It's easy to forget, and just because we don't count with 0, we start counting with 1. So be mindful of that. So what I'm going to need to do when I go to the table is I need, again, I'm going to go between these two, but I need the probability of 0, 1, 2, 3, 4, 5, and 6, and I'm going to need to add those together. So if you look here, I need to add the average of all of those together. Well, luckily these first few are really easy. They're 0. And if we keep 2 decimal places, these will also be 0. It's really only the last few that I have to worry about. So I need the average of 0.024 and 0.003 and 0.061 and 0.012. Oh, what the heck, I'm going to just average them all. So the average of these two is 0.001. The average of these two is 0.004. The average of these two is 0.0135. And the average of the last two here are 0.0365. Now I can add all of these together, and I end up with 0.005. 0.05. Again, if you do this on a calculator, you're going to get a slightly different answer. So the third part of this problem is 9 or more favor the death penalty. That's pretty straightforward. Anything 9 or more, so we're looking at x greater than or equal to 9. That means I need the probability of 9 plus the probability of 10 plus the probability of 11 plus the probability of 12 plus the probability of 13 plus the probability of 14 plus the probability of 15. All right, so we're going to go to our table. You'll find this will be much easier on a calculator when we do this in class. But for now, we're going to go to the table. That means I need all of these. And I go back here. And I'm going to take the average of all of those. So the average of 0.207 and 0.147 right here is going to be 0.177. Now I need the average of 0.186 and 0.206, and that is 0.196. Now I need the average of 0.127 and 0.219, and that gives me 0.173. Now I need the average of those two, and the average of 0.063 plus 0.170 is 0.1165, and the average of 0.022 and 0.032. Let's see, I need to look underneath that. Nope, 0.092. So 0.022 and 0.092 gives me 0.057. Now I keep covering these up. Okay, and the average between 0.005 and 0.031 is 0.018. And finally, the average between 0.000 and 0.005 is 0.0025. All right, and now we can add these up for a total of 0.733. All right, and the final part of this problem is we're looking for the probability between 3 and 9 favor the death penalty. So that's the probability of x, and we're including 3 and 9, greater than or equal to 3 but less than or equal to 9, which is going to be the probability that 3 favor it, plus the probability that 4 favor it, plus the probability that 5 favor it, plus the probability that 6 favor the death penalty, plus the probability of 7, plus the probability of 8, plus the probability of 9. So that's going to be adding up the values between 3 and 9. Why don't you pause the video and try it out yourself, and then turn it back on when you're finished, and we'll check your answer. All right, so you needed the probability and the average between 3 and 9. That's going to be the sum of all the averages between these values. And when I average all those values and add them up, I get 0.4375. So the probability of x greater than or equal to 3, but less than or equal to 9 from the table ends up being 0.4375. So I just realized that your book actually has 65% calculated for you. So you won't need to take the average. You can just add up the values in the column. You might get slightly different values because I'm using a different table, but as long as you get something fairly close, you should be good. Now, the next example, the next page of your notes, sorry, is shows 3 different methods for calculating binomial probabilities. There is table 3 that you've already used in your appendix. There's also table 4 in your appendix. Table 4 is when you're calculating an accumulation of probabilities. So the thing about that is you have to be careful. So I'm just going to draw a simple binomial probability. I'm just making up a picture of a binomial probability. Let's say this is the probability of 0, the probability of, so these are my x values, the probability of 2 successes, the probability of 4 successes, and here's my probability of the successes. So here's x, here's the probability of x. If I'm using a table and I go in and I look at the probability of 2, well, that's this right here. I'm really looking at one value, one column of my data. But if I go in and I'm looking for the probability of x less than or equal to 2, well, I'm looking for all of these values. And that's what I'm looking for, an accumulation of values. I'm looking for the probability of 0, the probability of, and the probability of 1, and the probability of 2. And the cumulative distribution table, probability distribution table, so this would be a cumulative. It goes and it adds those up for you. So you're not going down the column and adding each value. But you have to be careful, because when it calculates them, it calculates starting at 0, then 1, then 2. So it's calculating all of the values from 0 to 2. But if I wanted the values greater than 2, well, I'm not going to get that by looking at 2 in the table. I have to think about this a little bit differently. If I shade these in with a different color, so I'd be looking for these values here. Well, one thing about the probability, any probability distribution function, is that all of these have to add up to 1. So this plus this plus this plus this column here plus this column here plus this column here, that has to equal 1. So if I do 1 minus these values here, then I'm going to get all of the values here, right? So I have to think about this a little bit differently if I'm going to use the cumulative distribution function, and I need values that are greater than, or even values that are between. Let's say I wanted these values here. The values between, I wanted 1, 2, and 3. So remember that all of these add up to 1. Let me erase some stuff here. All of these probabilities add up to 1. So what I can do is I can find all of my values up to here, right? That's going to give me this column 0, this column 1, this column 2, and this column 3. So I can do the probability of x less than or equal to 3, and I could subtract this guy here, and that would leave me with these. So that's how you use a cumulative distribution table. The other way to do this is with Excel. We probably won't get into this in class, but if you're good with Excel and you know how to use it, you are certainly welcome to add on your homework or classwork. I would recommend, though, either getting familiar with the table or the calculator, because you won't be able to use a computer on an exam. And the last thing in that sheet of paper is using a TI 84 or 83, and we will be going over that in class. All right, so let's get to our second example. According to CITA, 25% of all U.S. households are wireless only. In a random sample of 20 households, what's the probability that exactly 5 are wireless only? So we're looking for the probability of 5. And if I go to my table with 20, where n is equal to 20, p is equal to 0.25, and I go to the x equals 5, I find that it's 0.023. So fewer than 3 are wireless only. So this time I could go to my cumulative binomial probability distribution table, and I don't have a picture of that in my slide presentation. So if you want to do that, you're going to have to figure out how to do that yourself. Or you can go to the other table we've been using and just add up the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. But from the cumulative distribution table, it looks like 0.2252. I've gone to n equals 20, probability is 0.25, and the column 3, and I get 0.2252. At most, 3 are wireless only. Ooh, I have to think about that. Oh, actually, I have to go back. This is 0.2252. I've made a mistake. I did not think this through carefully enough. This is where you have to be careful. Again, the warning is, if I were to talk this out, if I said, is 3 fewer than 3? No, I'd know that I'm looking actually for the probability of 2, of x less than or equal to 2, or just less than 3 would work as well. So I have to go back up to the table, but I already calculated this problem below it, and luckily I realized my mistake, but you'll need to be careful. So when I go to the table for 2 and I look at the cumulative distribution table for 2, that is actually 0.0913. So at least 3 are wireless only. Is 3 at least 3? Yes. I'm being more careful this time, you see. Is 4 at least 3? Yes. So if I use the cumulative distribution table, again, because it's going to calculate everything from left to right, and I need somewhere over here, I'm going to have to subtract this section. So at least 3 includes 3, so I want to, from the cumulative distribution table, subtract everything less than or equal to 2. And when I go to that, if I look at, I've already found what 2 or less is up here earlier on in the problem. I'm just going to subtract that value. And I end up with 1 minus 0.0913, 0.9087. So between 5 and 7, because there's only 3 values, I think it's easier perhaps to add them up from the regular table. So I'm going to go back to table 3 and find those values. Right, table 3 is the just the plain probability distribution function that finds the value at 1 success, and the cumulative was table 4, and that's where we were finding the value of 0 to some number. So if I look in my table, this is 0.203. The probability of 6 is 0.16, oops, forgot my 1686. And the probability of 7 was 0.0 1124. And adding those up, I get 0.484. All right, according to CITA, 25% of all U.S. households are wireless-only households. In a random sample of 300 households, determine the mean and standard deviation of wireless-only households. So this is really simple. It's just the number times the probability, and that's going to give us our mean. And we have 300 trials times 0.25 gives us 75. So 75 is our mean. Standard deviation is going to be the square root of NPQ. So we need the square root of 300 times 0.25, and then the probability of Q failure is going to be 0.75, because 0.25 and 0.75 equal 1, and I end up with a standard deviation of 7.5. Why do we care about this? Well, let's use it in a problem. In a simple random sample of 300 households, 92 were wireless only. Is this result unusual? Why or why not? So unusual is when we are plus or minus 2 standard deviations from the mean. So let's go ahead and see if we are. So 2 times our standard deviation gives me 15. If we are more than 15 away from the mean, our mean was 75. And that's 90. So anything greater than 90 is going to be unusual. So this is unusual because it's 92. Anything less than 75, or 75 minus 15, which ends up being 60. Anything less than 60 would also be unusual. All right, so in a simple random sample of 300 households, 75 were wireless only. Is this result unusual? No, because usual would be between 60 to 90 is usual. And 75 is right in the middle. And 75 also is the mean. So not unusual. All right, that's it for today. At least for standard deviation and mean. So a binomial distribution shape, if the probability is 50-50, the shape of the binomial distribution is symmetric. If the probability is less than 50%, then it's skewed to the right. And we talked about skewed being if I put an invisible string around my probability and it looks like I've yanked on one side or the other, then it's skewed in that direction. And it looks like I've yanked it over here, so it's skewed to the right. If the probability is greater than 50%, then my probability distribution is skewed left. And if you look here, looks like I've pulled it this direction, my string that direction, so that is skewed left. Just wanted you to have some idea of what a binomial distribution looks like. You'll be happy to know that's it for real this time.